Hello everyone, my name is Komasinyolo. Welcome to another video by Attention Matrix, where we try to make learning fun and easy. Please comment, like, and subscribe if you would like us to continue making this content and you enjoy it or find it helpful. Now on to the next video. Let's get right into it. In this lesson, we will be looking at convergent and divergent geometric sequences and series. Okay, these are a geometric series, as I've just mentioned, and they could either be of a convergent type or of a divergent type. So what does that mean? Okay, so divergent, divergent, and convergent. Convergent geometric pattern. I'm just going to say pattern. We're talking about sequences and series here. Okay. Divergent and convergent geometric patterns. Now, what does that mean? Okay, so let's start off with divergent series first, or divergent pattern first. Let's say you've got this following geometric sequence. You've got 1, you've got 2, you've got 4, you've got 8, you've got 16, etc., etc. Next one is going to be 32, etc., etc., etc. So remember, what makes a geometric sequence geometric is the fact that two successive terms, the ratio of two successive terms is constant. Okay, so this is not T2, this is actually T1. So you got T1, 1 is T1, 2 is T2, 4 is T3, 8 is T4, 16 is T5, and we know that the ratio R is equal to T2 over T1, which is equal to T3 over T2, which is equal to T4 over T3, etc., etc. Okay, and it all has to be equal, so all of these should give you the same value for R. So for instance, T2 over T1, T2 is 2, okay, and then T1 is 1. So 2 divided by 1 is 2, right? That's 2. Now what is T3 divided by T2? T3 is 4, T2 is 2, right? So T3 divided by T2 is equal to 4 over 2, and that's R. Okay, so that's equal to R, which is 2. This is equal to 2. Okay, and then those are the same, as you can see there, and it's gonna be the same case for all of them, right? So this is just a quick recap. The more detailed explanation of this is in a previous video. Okay, so now what makes a series divergent? What do we mean by divergent series or divergent sequence? Okay, what do we mean exactly by divergent? What does the word diverge mean? Okay, so a divergent sequence or divergent series comes from the word diverge, right? What do we mean when something diverges? It separates, okay? It spreads. It spreads and it separates, okay? It doesn't lead towards a singular point. It leads towards separate points. I'm going to explain what that means. So if I had to explain that using lines, if you start off with a point there, right, and then as you move forward, that point starts to spread into different paths and different directions, and it spreads and spreads and spreads, and it doesn't lead towards one single point. They just spreads to many different points. Okay, so that's what to diverge means. To diverge simply means to separate. If I have to put it nicely, it just simply means to separate. Okay, so what does a series or a sequence have to do with separating, okay, or spreading? That's another nice word you can use. It spreads. What does a sequence or a series have to do with this? What does a geometric sequence or geometric series have to do with things separating, right? Okay, well, I'm going to use the series that I just used right now. Okay, so the series that I just used right now, or the sequence that I just used right now, I had 1 as my first term, and I had 2 as my second term, and I had 4 as my third term, and I had 8 as my fourth term, and I had the next term being 16, and we know the next term is going to be 32, and so on and so forth. Okay, now if you look at this, what is our ratio? What is our common ratio? We calculated it before. Our common ratio R is equal to 2, right? Because any number divided by the number that comes before it is going to give you 2. Any number divided by the number that comes before it is going to give you 2. Doesn't matter which two numbers you look at, they're always going to give you 2, right? So our common ratio is 2. This means that if you want to find the next number or the next term in this sequence, all you have to do is take this the term that you have and multiply it by 2, right? If I only started off with 1, I have 1. How do I get to this number here, the second term? Well, you just say 1 times r, where r is 2, right? So then you're going to say 1 times 2 is 2. Now that I have 2, how do I get to the next number? The next number is 4, but I have 2 right now. So all I do is say 2 times r is equal to 2 times 2, and that's going to give me 4. Okay, and then how do I get to 8? I just multiply 4 times 2, which is r. 4 times 2, I just say that's 8. Then how do I get to the next number? That's 8 times 2, and then that's 16. Now, you will notice what's happening here. You will notice that for me to get to the next term, all I have to do is multiply the term that I have right now by r, which is my common ratio. Common ratio won't always be 2. It can be any number, right? It can be any number, but all I'm doing is I'm taking the term that I have and I'm multiplying it by the common ratio to get to the next term. Now, you will notice that as I'm doing that, as I'm multiplying each term by the common ratio, the numbers of the sequence or the series get bigger. In this case, it's a sequence. The numbers or the values of the terms of the sequence get bigger each time. They get bigger and bigger and bigger, and they don't lead to a certain specific value. So you've got 1, right? What is 1 times 2? 1 times 2 is 2. What is 2 times 2? 2 times 2 is 4. What is 4 times 2? 4 times 2 is 8. What is 8 times 2? 8 times 2 is 16. It's 16. What is 16 times 2? 16 times 2 is 32. What is 32 times 2? 32 times 2 is 64. What is 64 times 2? That's 128. You see what's happening? It's getting bigger and bigger, and it's showing no signs of slowing down. It's showing no signs it's showing no signs of stopping to get bigger. So it's always going to get bigger. The next number is 256. Then the next number is what is the next number? It's a bigger number. Then it's always going to get bigger. So in other words, you started off with 1, right? You started off with 1, and then you are getting bigger and bigger with each number. We're not approaching any specific number. We're always getting bigger, right? Or the numbers are very different in magnitude. The magnitude of the number is way bigger. It's getting way bigger than the one that you started off with. You started off with 1, already you have 256, and 256 is term number. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Already at T9. At term number 9, we are already at 256, whereas at term number 1, we were at 1. Okay, so this is what I mean when I say the series is spreading. It's spreading, it's separating, it's getting bigger and bigger. It's not leading towards a certain specific point. It's spreading, okay? It's getting bigger. And this is what we mean when we say this sequence is divergent. It diverges, right? It spreads, it separates, it's getting bigger and bigger, and it's showing no signs of slowing down. Now, this series that we are looking at right now is an example of a divergent. It's an example of a divergent sequence. This example here. Let's look at a different example of a divergent geometric sequence. Another one is, say we start off with 3, right? Then we have 9. Then we have 27. Then we have 81. This is where I'm going to stop. Okay. And then we go on and go on. Now, this is a geometric sequence. I'm telling you that it's a geometric sequence. How do I know that it's a geometric sequence? Because, well, I have T1 here. I have T2 here. I have T3 here. I have T4 here. Okay, T2 divided by T1 is equal to 9 divided by 3. That's going to give me 3. Okay, and T3 divided by T2 is equal to 27 divided by 9, and that's going to give me 3. These are my common ratios, and they're the same. Okay, so this is definitely geometric, no doubt. It's geometric. Now, you will notice that in this geometric sequence, these numbers, right? These numbers are getting bigger. We started off with a smaller number. We started off with 3, right? And then T2 was 9. And then T2 here is 9. T3 is 27. T4 is 81. It's getting bigger and it's growing very quickly. Already we're at T4 and we're already at 81 when we're still at T4, right? T1 is 3 and T4 is 81. So it's getting bigger. It's spreading very quickly. It's diverging. So this is an example of a divergent series. It's getting bigger and bigger and bigger, and it's showing no signs of slowing down. Okay, so that is what is happening with this series. Now, with this sequence. Now, what then do we mean when a series converges? Okay, now, what is a convergent series or convergent sequence? What is a convergent sequence? Now, convergent comes from the word converge, right? To converge, and this simply means to come together, or to move towards a singular point, or to move towards a specific one point, right? To come closer and closer and closer together, to meet. Basically, to converge is to meet at a certain point, right? So, if I look at that series that I used as an example before, I had that sequence that I used before, I had 1 and 2 and 4 and 8 and 16 and 32, right? You just keep multiplying each term by 2 to get to the next term. This separates. It separates, right? So remember, we looked at this and we said it was divergent because it separates. It spreads, right? It spreads. So it gets very big. It gets bigger and bigger and bigger and bigger and bigger. The magnitude of each of the number gets bigger and bigger and bigger. This was for divergent. So this is not convergent. This is divergent. These are the characteristics of a divergent sequence or series, right? For convergent sequence, we've got the following. Let's say we start off with, let's say we've got let's say we have 8, right? We've got 8 and we've got 4 and we've got 2 and we've got 1 and we've got 1 over 2 and we've got 1 over 4 and we've got 1 over 8, etc., and so on and so forth. Moving on to all the other other terms. Now, what is happening with this sequence? Well, first of all, I'm telling you that this sequence is a geometric sequence, right? How do you prove that it's a geometric sequence? Nothing changes. This is T1. We use the same approach that we've been using all this time. This is T1, T2. So if you start seeing fractions like this and weird numbers, stuff like this shouldn't intimidate you, right? Just as long as you understand the approach and you know the approach, numbers like this shouldn't intimidate you. Fractions shouldn't intimidate you, right? This is a geometric sequence. How do I prove that it's a geometric sequence? Well, you find R, and R has to be the same for any two successive terms or any two consecutive terms. So what is T2 divided by T1? What is T2? T2 is 4. What is T1? T1 is 8. So R in this instance is 1 over 2. If you punch this in your calculator, you'll get 1 over 2 or 0, 0.5. Okay, 0, 0.5 or half, right? What is T3 divided by T2? Well, T3 in this instance is 2, and then T2 is still 4, right? Still 4. 2 over 4 is 1 over 2. Okay, and this is going to give you half. So nothing changes. The approach is still the same. This is half, that's R. So this is indeed a geometric sequence. Okay, now what do you notice about this geometric sequence? Well, the value of your R in this geometric sequence is a decimal. It's 0, 0.5. 0, 0.5. It's a decimal number. Okay, so far the examples that I've been looking at, or the examples that I've been dealing with, are examples whose value of R has always been a non-decimal number. The number was not a decimal, and not only is it not not only were the values not non-decimals, but they were also bigger than 1 in all the instances. Okay, they were bigger than 1. If you notice this value of R here, let me just erase this. Okay, so if you notice here, this value of R here is less than 1. Okay, it's less than 1. This value of R here is less than 1. So for all the values that I've been looking at so far, the values of R have always been greater than 1. The magnitude of the values of R have always been greater than 1. But in this instance, this is the first sequence where the value is less than 1. And this is important, but I'll give you more clarity on why it's important as we move along this video. Now back to this sequence that we're looking at here. Okay, so notice what's happening. Term 1, just going to go back to the sequence. Term 1 is 8, right? Term 1 is 8. Term 2 is 4. Term 3 is 2. And then term 4, I'm just going to rewrite it again a bit more nicely. Term 1 is 8. Term 2 is 4. Term 3 is 2. Then we've got 1. Then we've got 1 over 2. Then we've got 1 over 4. This is where I'm going to stop. Now, you will notice what's happening. Let me just write this differently. You've got 8 as your first term, right? You've got 4 as your second term. You've got 2 as your third term, right? You've got 1. Then instead of writing 1 over 2 here, 1 over 2, you will agree with me, is the same as 0, 0.5, right? 0, 0.5. And then 1 over 4, you will agree with me, is 0, 0.25. 0, 0.25. Okay, if you punch 1 over 4 in your calculator, you'll see that it's 0, 0.25. And then the next number is going to be 1 over 8. 1 over 8. And you will notice that 1 over 8 is 0, 0.125, right? 0, 0.125. Now, you will notice that as I'm moving towards the right with this series, or with this sequence, the numbers are getting smaller and smaller each time. The numbers are getting smaller and smaller. We started off with 8. Let me change the color of my pen so that I can indicate things more clearly. We started off with 8. Then we got a smaller number, that's 4. Then we got an even smaller number, that's 2. Then we got a smaller number, that's 1. Then we got a smaller number, that's 0,5. Then you got an even smaller number, 0,25. Then you got an even smaller number, that's 0,125. Now, what do you notice with these numbers? Well, these numbers are all, number one, they're all getting smaller, right? They're getting smaller. The magnitude of these numbers is getting smaller each time. It's getting smaller. But not only are they getting smaller, these numbers are moving towards 0. We started off with 8, right? We started off with 8 as our term number 1, and we are moving with each term that follows. We are getting closer and closer and closer to 0. Okay, so we started off with 8, then we got to 4. 4 is closer to 0 than 8 is, right? Then after 4, we got to 2. 2 is closer to 0 than 4 is, right? Then 1 is closer, then 0,5 is even closer, then 0,25 is even closer, then 0,125 is even closer. So it tells you that the next term after this will even be closer and closer and closer to 0. We'll keep getting closer and closer and closer to 0. So now this explains why we call this type of sequence convergent. Remember what convergent is. If I had to show something that converges with arrows, you start off with something, right? You start off with something, and then say you've got lines that are coming from here, and those lines are moving towards a specific point, one specific point. What is that specific point that these lines are moving towards? Well, that specific point, I can call it 0 if I had to illustrate this graphically. That specific point is 0. So the lines are converging. In this instance, we're not dealing with lines, we're dealing with numbers. The numbers are converging towards a specific point. What is that specific point? That specific point is the number 0. Okay, so you've got numbers already that have a certain value, and as you move forward or as you progress along the sequence, those numbers get smaller and smaller and smaller, and they are approaching 0. Okay, this is the nature of all all convergent geometric sequences and series. If they converge, it means that they move towards 0. Okay, so essentially, if I had to give a very simplistic explanation of divergent and convergent, divergent moves, divergent series and sequences, they move away. They move away from 0, right? They move away from 0. And then convergent sequences and series, convergent sequences and series move towards, they move towards 0. They approach 0. They move towards 0. This is a very simplistic definition of what a divergent and a convergent series is and sequence is, right? So if you remember this, it should be enough to make you understand when a series is divergent and when a series is convergent. The magnitude of the terms either move towards or away from 0. Okay, now let's add these series. Let's add these series. Remember, in the previous video, we dealt with geometric sequences and we dealt with series. We dealt with geometric series. Now, we said that the formula for a geometric series is Sn is equal to A, open bracket, 1 minus r to the power of n all over 1 minus r to the power of n. Okay, so this is the equation for a geometric series. Okay, if you want to add the terms of a geometric series, this is what you are going to use. Now, remember what the different components or the different terms or variables in this equation are. This is the first term, A is the first term, R is the common ratio, N is the position of the term that you're looking at. Okay, nothing changes. You know, you are familiar with this. You know it, and okay. So now let's add let's add the terms in our series. Okay, so let's say you've got a divergent series. So I'm going to give you a divergent geometric series. This is 1 plus 2 plus 4 plus 8 plus 16 plus 32, and so on and so forth. You can tell me now, if I ask you, is the series divergent or convergent? You will immediately tell me that it's divergent. Why? Because we started off with 1 and already we are at 32. You can clearly see that we are moving further and further and further away from 0, so this is divergent. Now, if I asked you to give me S7, well, you'd simply use that equation. You'd say A is equal to 1 minus r to the power of 7 over 1 minus r. And then you'd substitute the value of r there, the value of r there, and the value of a, and then you'd simply solve. Okay, I'm not going to solve this. We did this in a previous video. Right. Now, if I give you another divergent series, right? If I give you another divergent series, I'm just focusing on divergent for now. If I say 2 plus 4 plus 8 plus 16 plus 32. Same thing, right? And I asked you to find S8 or whatever. I asked you to find S8, right? You would take that equation and then you would substitute you would substitute into this equation and then you would solve, right? You would solve. You would solve and then you would get your answer, right? Okay, now what if I asked you to add the terms of a convergent series? Let's see what's going to happen. Let's see if we get anything interesting happening. Right. Okay. So let's say I'm going to use, which one must I use? I'm going to say 4. Okay. Plus 2 plus 1 plus 1 over 2. Remember, don't let fractions intimidate you. Plus 1 over 4 plus 1 over 8. Okay, this is the one that I've been using. Okay, so now what if I asked you to add this series? Okay, what if I asked you to find, let's say find S3. Okay, well, you can use the same formula. Remember what the formula says. The formula says, just before I actually substitute things, the formula is Sn is equal to A, then open bracket 1 minus r to the power of n divided by 1 minus r. Okay, now I substitute S3. What is S3? I substitute 3 and all the relevant terms. Well, A is 4, right? Because A is my first term, so A is 4, and then 1 minus R. What is R? R is simply T2 divided by T1. We know in this instance it's half, so that's going to be half, or that's going to be 1 over 2, and then to the power of n. In this case, n is 3. Don't let fractions scare you. Fractions are simply, they're numbers as well. They're just normal numbers. They just have decimals in them. Okay, and then you can punch this in your calculator and then you will get your answer. Okay, so you follow the exact same approach. You can use this equation, you follow the exact same approach, nothing changes. It's still a geometric series, so you're still using the sum of a geometric series equation to solve for this geometric series. Now, this is still S3. S3, you will agree with me that is still, you're still dealing with numbers that are at the first few positions of the sequence or the series that you're dealing with. S3 is simply adding the first 3 terms. Now, what if I ask you to add S1000? Nothing changes. You do the same thing. You take the equation S, then wherever you have N, you're going to substitute 1000. You use the same equation, you're going to get the same answer. Okay, now remember what I said. Remember what I said with a convergent series, right? I said earlier on that with a convergent series, if you're dealing with a convergent series, you're dealing with a series that moves towards 0. I'm going to keep repeating myself. It moves towards 0, right? Moves towards 0. It moves towards 0. Now, let's see what happens if I keep moving, if I keep adding terms to this convergent series. What's going to happen? It's going to move towards 0. I already told you that. It's going to move towards 0, but it's never actually going to get to 0. It's never going to arrive to 0, but it's going to be so close to 0 that we might as well say it eventually does arrive at 0. It never actually does arrive, but we're pretending as if it arrives at 0. Now, let me show you what I mean. Okay, so we've got, I'm going to use a convergent series. I'm going to use, let's try to use a different one this time. Let's say, uh, let's start with, let's say 9, right? 9, and then we've got 3, and then we've got 1, and then we've got 1 over 3, and then we've got 1 over 9, and then we've got 1 over 27, then we've got the next one is going to be 1 over 81, then the next one is going to be 1 over, let me just use my calculator here, 1 over 243, 243, then the next one is going to be, I want to show you something. Next one is 1 over 729. Okay, so if you notice what is happening, like I said earlier on, if I ask you, is this series divergent or convergent? Well, you will tell me that, okay, comma, I started off with 9, and then I got smaller, right? And then I started moving closer and closer to 0. I started getting closer and closer to 0. Started getting closer and closer to 0. What is 1 over 3? 1 over 3 is 0,333. And what is 1 over 9? Let me just show you what I mean. 1 over 3, 1, let me just erase this so I can write it more nicely. Okay, so we've got 9 as my T1, right? We've got 9 as my T1. Let's just do this. T1 is 9, right? T2 is 3. T3 is 1. T4 is 1 over 3. T5 is 1 over 9. T6 is 1 over 27. T7 is 1 over 81. T8 is 1 over 243. And T9 is 1 over 729. Now, if you look at these fractions, what is 1 over 3? Just so I can write them in numbers. 1 over 3 is 0,3, right? 0,3 recurring. So the 3 is recurring. So that's 1 over 3. And then what is 1 over 9? 1 over 9 is equal to, what is 1 over 9? It is equal to 0,11111. 0,11111. So it's 0,1 recurring. Okay, so what is 1 over, after 1 over 9, we had 1 over 27. What is 1 over 27? Well, 1 over 27 is 0,037. 0,037. Notice what's happening here. We are moving towards 0 each time, right? We started off with 9, then we had 3, then we had 1, then we had 1 over 3, which is equal to 0,3, then we had 1 over 9, which is equal to 0,1, then we had 1 over 27, which is equal to 0,037. Now we're moving closer and closer and closer to 0, like I mentioned. So this is a convergent series because it converges towards 0. It moves towards a certain point. Now, as we are adding, as we keep adding these numbers, it'll get to a point where we're going to be adding values that are very close to 0, that they're not going to be making a difference. We might as well not be adding anything. They're not going to make a difference, right? So let's say I ask you to add term number 1 million, right? If I ask you what term number 1 million is, term number 1 million will be it won't necessarily be 0, but it will be very close to 0. It will be very close to 0. So it means that in this series, we will get to a point eventually. So let's say, I'm going to say you have term 1, then let me just erase that and use pluses because I'm dealing with series. You've got term 1, right, plus term 2, plus term 3, plus term 4, plus, 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 plus. So you got plus term whatever. So let's say you get to a point where you've got term infinity, right? Term infinity is a term that is so far ahead. It's very, 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 very far ahead. It's so far that it's too far for us to get to by writing all the terms individually up until we get to that term. Now, you will agree with me that if I start off with a certain number, and the more I move along this series, I'm getting closer and closer and closer to 0. You will agree with me that by the time I get to the end, now the end is very, very far. It's very, very far. The value in the end of that term will be almost equal to 0. It will be almost equal to 0, right? So if we add the terms, the individual terms of this series, we'll get a number. In the beginning, we'll get big numbers, right? In the beginning, we'll get numbers that we can work with. So for instance, for this series here, we started off with 9. 9 plus 3 is a big number. It's 12. Then 12 plus 1 is 13. Then 13 plus 1 is whatever, right? So let me show you with this series. Actually, it's gonna get to a point where adding successive terms is not gonna be making a difference. But let me show you. Let me show you with this series. Actually, instead of just saying it, let me show you. Okay, so we have 9 plus 3 plus 1 plus 1 over 3 plus 1 over 27 plus 1 over 81. This is where I'm going to stop, right? If you take your calculator and you start adding these numbers, what is 9 plus 3? 9 plus 3 is 12, right? What is 12 plus 1? 12 plus 1 is 13. What is 13 plus 1 over 3? Well, that's going to give you 13, 3. Well, what is 13, 3 plus 1 over 27? That's going to give you about 13, 4. What is 13, 4 plus 1 over 81? 1 over 81 plus 13, 4. That's going to give you 13,41, right? 13, 41. You see what's happening here? The more I'm adding, so in the beginning, as I'm adding the terms in the beginning, right? As I'm adding the terms in the beginning, the numbers are changing slightly, but they're changing, right? So we moved from 12 to 13. And then from 13, we added the next term. We got what? 13,3. Then we added the next term. Then we got what? 13,4. Then we added the next term. Then we got what? 13,41. Do you see that the sum is changing less and less? It's changing bit by bit. Bit by bit, it's changing. Bit by bit, it's changing. It changes a lot in the beginning, and then it changes less and less as we move forward. We got 12, then 13, then 13,3, then 13,4, then 13,41. It's going to get to a point where, because what we are adding to the numbers is becoming so small, it's becoming so little, it's becoming closer and closer, and it's getting closer and closer and closer to 0, that adding it is not going to be making a difference. Already, we've added just 5 times here. We added just 5 times, and already we're getting to a point where we're experiencing very little change in the answer that we're getting from adding. Okay. Now, as we move and move and move further and we add, we're going to get to a point where adding is not going to make a difference. And this is where we get to a point where we're adding towards infinity, or towards term infinity. This is the infinity sign here. As we're moving towards infinity, our sum is gonna be more and more unaffected by the numbers that we're adding. It's gonna be less and less affected. Okay, now how do we know the actual number, the final number? Let's say, how do we actually know the final number that we are going to get to that is not going to be changing as we add more and more terms to it? Well, what do I mean by that? I'm saying we know that if I say S7, I know that I want you to add the first 7 terms of the series, right? If I say S8, I want you to add the first 8 terms of the series. If I say S20, I want you to add the first 20 terms of the series. If I say S54, I want you to add the first 54 terms of the series. Now, what about infinity? Okay, what about infinity? Right, because we have term infinity. What about infinity? What is S infinity? What does it mean? What does it mean? What does S infinity mean? Well, S infinity means add the first infinity terms of the series, right? Take all the existing terms of the series and add them together and see what you're going to get. What answer you're going to get? Well, we know that since this is a converging series, since the terms of the series, the successive terms of the series all add up to well, they don't add up to 0, they move towards 0. We know that as we move towards infinity, as we move towards term infinity, that we're going to be moving towards a certain number. Remember, we were moving towards 13 point, for the series that we were looking at, we had 13, and then we had, as we were adding, we had 13, then we had 13.3, then we had 13.4, then we had 13.41. This is for the example that we were doing just now. Do you see that we're changing less and less? We're moving less and less away from 13, and we're moving towards a certain value, 13.4 something something something. That's the value that we're moving towards. Well, how do you get to that value without actually adding the individual terms like we did? Okay, so you will notice something. You will notice something with the example that we just did right now. You will notice that, let's say, I'm going to use the same sequence again. We had 9. I'm going to use the same series. We had 9, we had 3, then we had 1, then we had 1 over 1 over 3, then we had 1 over 9, then we had 1 over 27. Okay, etc., etc., etc. Now, how do you find Sn? Not Sn. How do you find the sum to infinity? How do you find the sum of the first infinity terms of the series? So you keep writing all the terms up until you get to infinity. You keep writing them up until you get to infinity, and we all know that we will never reach infinity, right? We'll never reach infinity. You're going to keep writing and writing and writing and writing and writing up to infinity. Now, we know that from our equation, we had a, right, open bracket, 1 minus r to the power of n all over 1 minus r. We are familiar with this equation, right? In this case, I have infinity. So remember, this value has to be the same as that value there. So n has to be the same. So if I substitute that value in this equation should be familiar to you right now. So we've got S infinity, right? The sum of the first infinity terms is equal to a, then 1 minus r to the power, instead of n, I'm going to write infinity, then close bracket, 1 minus r. Right. Now, for this convergent series, let's say I'm gonna find our common r. What is our ratio? This is a geometric series. Remember. So if I scroll back up there, what is our value of r? Remember, r is t2 divided by t1, or the ratio between two successive terms. So this divided by that, or this divided by that, or this divided by that. Okay, so that's going to be 1 over 3. R is equal to 1 over 3. So 1 over 3. Okay, this is our ratio. That's 1 over 3. Or you can also write it in its decimal form. That's 0, 0.3. I'm going to stop it here. 0, 0.3. Okay, so now we can substitute stuff into that equation. Okay, we've got sum to infinity of this geometric series is equal to a. A is 9, right? A is 9. Then we've got 1 minus r. R is 0, 0.3 to the power of infinity. Then divided by 1 minus 0, 0.3. I just substituted stuff into that equation. Now, what is the answer to this thing? Well, what is 0, 0.3 to the power infinity? We don't know what that is, right? We don't know what that is. What is 0, 0.3 to the power of infinity? What is that thing there? This thing here. 0, 0.3 to the power of infinity. Well, let's test different values. Let's say we had 0, 0.3 to the power of 1. 0, 0.3 to the power of 1 is 0, 0.3. Okay, cool. What is 0, 0.3 to the power of 2? If you take that and you punch it into your calculator, you will see that the answer that you get is 0, 0.09. 0, 0.09. What is 0, 0.3 to the power of 3? Well, we're getting bigger and bigger. You'll notice that we're getting bigger and bigger with our exponents. 0, 0.3 to the power of 3 is 0, 0.027. 0, 0.027. Okay, cool. That's fine. What is 0, 0.3? What is 0, 0.3 to the power of 4? Well, 0, 0.3 to the power of 4, 0, 0.3 to the power of 4 is equal to 0, 0.0081. Okay, 0, 0.0081. What do you notice happening here? We're getting closer and closer and closer to 0, right? 0, 0.3, then 0, 0.09, then 0, 0.027, then 0, 0.0081. We're getting closer and closer and closer to 0. Now, you will agree with me that as the exponent increases, okay, from 1 to 2 to 3 to 4 to whatever, as it gets bigger and bigger, as the exponent of this decimal gets bigger and bigger, of this common ratio gets bigger and bigger, 0, 0.3 to the power 70, say for instance, this is going to be even more closer to 0, more close to 0 rather. It's going to be more close to 0. It's not going to be 0, but it's going to be very close to 0. It's going to be 0, 0.00000 something, 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 but it's going to be very close to 0. So since the exponent makes that get closer and closer to 0, since this exponent here makes this entire value get closer and closer and closer to 0, then you will agree with me that we might as well make this entire thing 0. We might as well make this entire thing 0, because infinity is very, very big. Infinity is very, very big. And as our exponent gets bigger and bigger, our answer here gets closer and closer to 0. So if our exponent is very big, then it means that this will be very close to 0, that we might as well call it 0. Okay, so that leads me to doing something. If this is going to be the case, if that's the case, then we might as well not have that term in this equation then. We don't want that term in that equation because we're wasting time. If we're finding a sum to infinity, and we know that if we take infinity and put it as an exponent for a convergent series, then we might as well use 0 in place of r to the power of n there. So then our equation changes. What does our equation become? Well, we've got a sum to infinity is equal to a open bracket 1 minus, now I'm not going to say r to the power of infinity. Why am I not going to say r to the power infinity? Because r to the power infinity is close to 0. We just proved that now. So I'm not going to say r to the power infinity, but instead I'm going to say 0. I'm going to put in 0 there, divided by 1 minus r. I'm using the equation that we've been using this entire time. I'm just substituting 0 in place of that term because we're getting closer and closer to 0 for convergent series. Remember, this is for a convergent series, right? This is for a convergent series. Now, what we have is this simplifies our equation to, now what is this? What you have here on top here is just going to be a times 1, right? So that's going to be a over 1 minus r. And then we got this equation here. Now, what is this equation? This equation you will get in your formula sheet. This equation is your sum to infinity. You use this equation for a geometric series if they ask you to calculate the sum to infinity of a geometric series. Okay, if they ask you to calculate the sum to infinity of a geometric series. Now, how do you know if you're dealing with a convergent geometric series? You only use this for convergent geometric series. Only for convergent. Okay, for convergent. For convergent series. Convergent geometric series. You only use it for convergent geometric series. You don't use it for anything else. Remember, only for convergent geometric series. Now, how do you know that it's a convergent geometric series? Well, a series is convergent if, okay? Now, this is the rule that you must remember. A series, a geometric series, I'm dealing with a geometric series. So a series is convergent. So in other words, the terms will get closer and closer and closer to 0. A series is convergent if r is greater than -1 and less than 1. Okay, if r is greater than -1 and less than 1, what is r? R is your common ratio. If your common ratio is greater than -1 and less than 1, then your series is going to be convergent. Do not forget this. This is very important. This is very important. Okay, very important. Otherwise, your series is not convergent. If r is not within this range, then your series is divergent. Okay, so if r falls outside of this range, if r is not between these two values, then your series is divergent. Okay, so that's what it means. Let's do a quick example of sum to infinity. Okay, I'm going to use the series that I've used before. I think this is the series that I used: 4, 2, 1, 1 over 2, 1 over 4, etc., etc. Now, they say find the sum to infinity of this sequence. I gave you a sequence here. I'm telling you that it's geometric, and I'm asking you to find the sum to infinity of this geometric sequence here. Well, what I'm saying to you is basically, this is what I want you to find: 4 plus 2 plus 1 plus 1 over 2 plus 1 over 4 plus up until I get to term infinity, which is very, 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 very far away, right? It's very far away. Now, how do you find that? Well, you just use the equation for sum to infinity. Now, if you want to use, listen, if you're not sure if this whole sum to infinity thing is confusing to you, use the equation that you are used to. Use this equation, right? If it confuses you, you can use this equation, right? 1 minus r to the power of n. This equation is all encompassing. It works all the time. It works all the time. It's not wrong. It's never going to be wrong, right? The sum to infinity equation is just a simplified version of this equation. So sum to infinity, you can say sum to infinity is equal to the first term is 4, and then 1 minus r, and then r in this instance is, what is r in this instance? Let's go up and see. R is equal to term 2 divided by term 1. That's 2 over 4, that's 1. Or term 3 divided by term 2 is 1 over 2, right? So that's 1 over 2. So this is, let me just remove this line that I drew in right now. Go away. Okay, so 1 over 2 is our r. So our r is 1 over 2 to the power of infinity, right? To the power of infinity all over 1 minus r. Okay, and then we know that this is 0, right? This is going to be very close to 0, so it's a waste of time including it there. So all we've got is 4 over 1 minus 1 over 2, because r is 1 over 2, right? And then we can solve this. We'll remove you. Let's scroll up. Okay, so when we solve this, what we get is 4 divided by 1 over 2, which is, if you punch this in your calculator, it's going to be 8. Right, so what does this tell me? Well, this tells me that if I look at this series here, if I look at this series here and I keep adding terms and I keep adding terms forever, I add them forever, the answer that I will get to eventually is 8. Is very close to 8. I'm not going to get an answer that is bigger than 8, right? I'm going to get an answer that is very, very close to 8. So the sum to infinity is 8. As I'm adding each term to the term that comes before it, I'm going to get to a point where the terms that I'm adding are very close to 0. And because they're close to 0, the number that I'm adding those terms to will be very close to 8. So I might as well call it 8. The sum to infinity is 8, right? Now, if you were to do it the proper way and you were to use the equation that I derived for you, this is how you would do it. You say sum to infinity is equal to a over 1 minus r. And then you substitute into this equation. This equation will be in your formula sheet. You just need to know how to use it and understand when to use it and when not to use it. Okay, so if you substitute stuff into this equation, what you will get is, what is a? Remember, a is 4, and then over 1 minus r. R, we calculated it, is 1 over 2, which is basically what we had on top. Okay, so 4 divided by 1 over 2, and that's going to give you 8. And then this is your answer. This is your sum to infinity. Okay, so this is how you do your sum to infinity. You just take this equation and then you substitute the terms that have been given to you, and then you get your answer. And that's basically how you solve this. Now remember, you only use this equation if you are dealing with a geometric convergent series. It has to be geometric and it has to be convergent. How do you know that it's geometric and it's convergent? Well, for you to know that it's geometric, you have to make sure that r is the same. That's for you to make sure that it's geometric. How do you make sure that it's convergent? You make sure for convergent series, I'm going to keep repeating myself to hammer this home. For convergent, r has to be between -1 and that. This is the only time you're allowed to use this form of the equation. The only time. Okay, if they ask you to find sum to infinity, you use this equation. Only ever use this equation. Only use this equation if r is greater than -1 and less than 1. Okay, for a divergent series, there is no such thing as a sum to infinity. Okay, so just make sure that you remember that. For divergent series, there is no such thing. There is no sum to infinity. It does not exist. So whenever you're dealing with a divergent series, remove this from your head. It does not exist, okay? Because you don't move towards a specific value, you don't move towards a specific number. You're moving further and further away from zero for a divergent series. You're not moving towards zero, so it's not convergent. You can't have a sum to infinity. The rules don't apply. Okay, so just make sure that you understand that. Okay, so that's what the sum to infinity is. That's a divergent series, and that's a convergent series, and that's what they mean. And just basically, essentially know which equation to use for which scenario, and know how to identify if something is convergent, if something is divergent, and if the series that you're looking at or the sequence that you're looking at is geometric. And yeah, we will cover a couple of more examples on a separate video, or we'll solve a couple of exam questions on a separate video. But this is essentially all you need to know, the most basic things that you need to know about this topic. We will cover other topics on separate videos. Till next time. Lesson number one, lesson number one. Lesson number one, lesson number one.